smarter cities using the Nordic Thingy 53 to prototype predictive maintenance applications. I'm David Tischler. I'm a developer program manager at Impulse. You may recognize me from some other community events and other community work as well. But today I'm presenting the Nordic Thingy 53. So let's go through a quick agenda and outline. Now, I am going to move pretty quickly here. I'll try to get to questions as they pop in. Anything that I link to or anything I show off here, I'll make sure that we have all of the links into the description of the video, and there's full documentation on everything. So if you miss something along the way, no need to worry. And actually, I believe it's also being recorded, so you could watch it on demand later. So here's what we'll talk through today. Number one, of course, who's Nordic Semi and what is predictive maintenance? We'll go through the Thingy 53 hardware. We'll talk about building machine learning model in Edge Impulse and deploying the model onto the Thingy 53. And then I want to kind of talk about the prototype to production process and scaling. We will walk through the process with our slides, so I'm going to bore you for a little while. Then we're going to attempt a live demo. We'll see what happens, but I've said my prayers to the demo gods, and I'm hoping they'll take the offering. Then we'll come back to the slides, wrap up, and get to any questions. I'll try to grab questions along the way as well. We'll see how successful I am. To start off with, though, who's Nordic Semi? So they're an MCU semiconductor company empowering wireless innovation, and they build chips for the Internet of Things and edge devices. There's cellular IoT, Wi-Fi, Bluetooth, BLE, Matter, Thread, Zigbee, and more. They build SoCs, developer kits that are the more prototype platform boards, and then finished prototyping products that are turnkey ready to go. And you can see a couple screenshots here of you can, just go to the SoC, or you can see how a development kit comes, kind of like a PCB you'd be familiar with. And then predictive maintenance. Let's define that a little bit. So manufacturing, industrial assembly lines, these types of equipment need regular maintenance, regular upkeep, regular servicing. And in most cases, there's planned downtime, but unfortunately, as you probably know, breakdowns can occur. And when a breakdown occurs, it's a reactionary process to repair it. It's expensive, it's disruptive, and in business that can mean lost revenue, which is not ideal, but it's also not life-threatening. But like Alex mentioned at the beginning, city services are different. That could mean disruption to clean drinking water, wastewater removal, trash collections, communications, traffic management, or other infrastructure services, and that can have severe consequences. So predictive maintenance can help address some of this by taking care of or using machine learning to help understand the health of a machine before it breaks down. It can understand what an object should look like, what sounds would normally be heard, or when an action or movement should or should not be occurring. And as I mentioned, the goal is to take action before the equipment fails and a breakdown occurs, and then plan for that downtime. Now, when I saw Impact Summit announced, that I attended last year, I think I even presented last year as well. When I saw it announced, I thought, interesting. How can I participate? And I had just read about, as I mentioned, I think in the comments earlier, I'm in Phoenix, and it is hot here. It is the desert. And I had just read this article about an expansion of our underground cooling system. And what we do in Phoenix is a shared service, a shared air conditioning that uses pumping stations underground under downtown Phoenix. And this system feeds about 40 to 50, tall buildings, skyscrapers, and it's being expanded with a new $50 million pumping station, cooling plant, they call it. Pretty neat. So the way it works is underneath the city, underneath street level, they have these large holding tanks all throughout across the blocks, the city grid. And overnight, they freeze these tanks of water. And during the daytime, when the ice melts, they pump it and push the cold air coming off of the melting ice blocks up into the buildings to provide the air conditioning. So Chase Field, that's the big ballpark, the convention center, there's hotels, and then office buildings throughout downtown. And you can see some screenshots. These came from that article. So this is a pretty neat setup they have down there. And as I was reading through, they needed the additional capacity, of course, just for general expansion, but they were talking about how to then use this new pumping station as a failover for the existing system. And, I kind of started thinking, well, from a predictive maintenance perspective, that makes sense. That way they can take some of the systems offline, use the new station to then, generate the capacity to keep the rest of the buildings cool while working on the others. And I started to think about, I wonder if I could build something like that. Now, I didn't want to break and enter the facility. There's jail time associated with that. I wasn't really interested in that, so I couldn't prototype there. But essentially, it's a closed loop water system that just freezes and then pumps back and recirculates. And I thought, well, you can get smaller scale pumps on Amazon pretty cheap. And I know that the Thingy 53 has an IMU, an accelerometer, an inertial measuring unit. I could prototype this and just see if theoretically I could build a predictive maintenance system that could function at city scale. So sure enough, I got on Amazon and got some parts together, including a pump, a variable speed pump, which is important because we'll come to that in a few minutes, and a Thingy 53, and built myself a closed loop system. And I've got it here. Let's see if I can figure out how to switch cameras that Alex had gotten a sneak preview of. Yep, sure enough, there it is. And I'll come back to this in a moment. Here's another angle. It's turned on, it's running right now. So let's talk about the Thingy 53. And it's a multi-sensor prototyping platform designed for rapid wireless IoT and embedded machine learning development. It's neat. It's just a couple inches square in a nice sturdy plastic housing, and contains obviously the NRF5340 SoC, which is a dual Cortex M33 setup. It's got, like I talked about earlier, Bluetooth LE, Bluetooth Mesh, NFC Thread, Zigbee, and 2.4 Wi-Fi. Quick Stemma Grove compatible. It has a battery already included. You can just charge it via USB-C. It's got LEDs on board, a couple of buttons, and it's got the 6-axis accelerometer, which we're going to make use of. There's also temperature, humidity, air quality, air pressure. I didn't need those in this particular case, and a microphone as well. So it can be used for wake word, keyword spotting, and other audio machine learning projects. So where are we on the agenda and also on time? Let's see, we have covered who is Nordic. We've covered the Thingy 53. Let's go through the process of building a machine learning model. I'm going to show this again in slide format, but then we'll drop out and go over to the Edge Impulse Studio in a few minutes. Let's start with the slideware though. In a typical machine learning project, when using Edge Impulse, you have 4 distinct phases: collecting your data and building a data set, designing your model, your algorithm, testing in order to validate that the model actually functions, and then deploying it to the edge device. In our context, for prototyping this predictive maintenance solution on the pump, I want to collect movement and magnetometer sensor data. And I'll come to the magnetometer in a few minutes as well. We're going to then build the model to recognize the movement and magnetic field, measure the accuracy with a quick test, and then we can deploy it directly onto the Thingy 53 for on-device local machine learning. There's no cloud connectivity. The first thing to do is to go to Edge Impulse, create an account if you don't have one, or log in if you do, simple studio.edgeimpulse.com, and create a new project. And you can choose between a developer account or an enterprise account. The developer plan is free. The enterprise is a paid plan. There's a 14-day free trial, but the developer account is all you need for something like this. We come to the dashboard, and the first thing we need to do after that is collect our data set. There's a couple different options for generating a data set. You can upload existing files if you already have them. You can capture new data directly from the studio. You can connect to buckets, S3 buckets or Google Cloud Storage. You can even clone existing projects that have data. But for this workshop, we're going to capture data directly from the Thingy 53 because I want data that is coming from this particular pump used with the Thingy 53 accelerometer. I don't want to, try to adapt other data. So I need to connect the device, connect the Thingy 53 to Edge Impulse. The Thingy 53 comes out of the box ready to go with Edge Impulse firmware already installed. Now you can certainly flash other firmware to it, but it comes ready to go off the shelf with Edge Impulse firmware on it. And you can install a little bit of tooling. There's a CLI available for Mac, Windows, or Linux. I'm not actually going to use the CLI though, because there's also an app that can be installed on iOS or Android. In my particular case, I also have the luxury of being on a Mac, which will put a wrapper around the iOS app, so I can run the app straight from my computer. It's pretty neat, and I'll show that too in a few minutes, and connect it to the EI Studio. It will appear in the studio first under the devices tab. In this particular one, I can see it's red, it's not connected yet. But if I go into the app and click on connect, it'll connect over Bluetooth. And then it will, you can see the green dot is now here, the status is connected. And I can do data acquisition, and this is exactly what I want. I want to take samples from the pump in the idle state and the running state. And I'm taking 10-second long incremental samples. You can also do it in the studio. Similarly, it's pretty easy. You just label what you are going to collect. Like in this one, I have the running state, and I've chosen what sensor. Like I said, there's also temperature, humidity, the microphone, but I want the inertial sensor. And I hit the start sampling button, and you can kind of see the waveform that came off from that particular data sample there. Then I need to build the model. And what we call an impulse consists of 3 main building blocks: the input block, the processing block, and the learning block. And there's default recommendations, or you can customize all of this. I'm sticking with the default recommendations. They're typically fine. And I can see that in the processing block, the accelerometer XYZ and the magnetometer XYZ are being selected. Continuing through the process, you can see the DSP results. I'm not going to really dive into this too much here. And then it's time to actually build the classification model. And again, I'm going to leave the default selected, but there's an expert mode, there's options, there's settings, and it's all documented in the Edge Impulse documentation repo. But at the bottom of the page, you click on Start Training, and it'll start running through the iterations of building the model for you. At the end of that, and again, I'm in the Edge Impulse Studio here, but this can all be done in the app as well, and I'll show that. But at the end of the process, you come away with a validation set that it'll test against. It said I got 100% accuracy. It might be a little generous, but you can see actually that my data has been separated out into really nice clusters. To be fair, it's pretty easy to determine if the pump is running or not running. The data that was collected, it's separated in a nice way. We saw on that one data set that I had on the screen that motion across that 10-second sample size. When the pump is idle, obviously that's not there. So the model can tell pretty reliably if the pump is on or off. But I'm going to get to one additional feature next that is critical in predictive maintenance, which is anomaly detection. Sure, we know if the pump is on or off, but what we really want to know is if the pump is acting, I'll call it, strangely. And that's where the variable speed motor that I got is important. So we know right away that there are clusters, like I said, for idle or active, or the pump running. And we can see these clusters here. And if a data sample during live inferencing, once the model has been deployed to the device, if a sample falls into an abnormal range or zone, then that's what we consider an anomaly. I'll demonstrate that in a few minutes, but that's the whole point then of predictive maintenance. Is there an anomaly, and should it be investigated? Now, I went through a lot of information. I think I did it in 16 minutes, okay? But don't worry, everything I just covered, like I said, is documented. All of that was available in the Edge Impulse Studio, but as I've said, it's also available in the app. And the NRF app really simplifies what I just showed. On the left, there are devices. That's where you connect your thingy. There's data acquisition, which I showed, which will allow you to collect samples. And then there's deployment, which will allow you to build the model. And we simplify it down to just 3 steps: the compiler, the classifier, and the build. Admittedly, we lose the anomaly detection there, which is important, and that's why I wanted to show it in the studio as well. But once I've got it configured in the studio, then you can just use the app for later builds. So let's check on our agenda. And actually, I'm going to take a moment to pop over to see if we've had any questions come through. I'll take a little pause here for some Q&A. When can we expect NRF 54 public availability? Well, you're going to have to refer to Nordic on that one. I did see the NRF 54 announcement on their homepage, so definitely want to go have a look to see if they've released or have provided a date there. Justin has asked, what is the best way to wirelessly collect data? That is a great question. That is going to depend a little bit on availability of connectivity in your development platform location, or B, final device location. So if your final device, now I'm showing predictive maintenance, but if your final device or final project is out in the wild doing, let's say, keyword spotting for an environmental project, I shouldn't say keywords, I should say audio detection, perhaps the sound of a chainsaw when it shouldn't be in a forest, or, poaching projects where you're listening for gunshots or wildlife noises and calls and things. You're not going to have Wi-Fi out there. You may not have rangers in the park in proximity of Bluetooth at all times, so you may need to use the dev kit bare board in order to interface with LoRa connectivity or NB-IoT or something like that. So it really comes down to where the device is going to live and what connectivity you've got available to you. For collecting data for this project, I had the luxury of being right next to the device on my desk, so I did it all over Bluetooth. But yeah, you're going to need to consider where your device is going. Let's see. When using Edge Impulse, what is the minimum data set you think one can use to get a good and accurate model? I'll show you in just a moment. I collected 18 minutes worth of data, 104 samples, if I remember correctly, to build this model. And this model came out extremely accurate. So I probably could have gotten away with a bit less, but data is critical when building a machine learning project. It is absolutely critical for the quality of the model that comes out the other end. So the general answer is the more data, the better. I probably could have gotten away with about 10 minutes worth of collected data in this case, maybe 60 samples, but just to make sure things were working, I went a little higher. Let me see. Are you able to select, add, or modify Python or C++ packages with the Nordic 53? Yes, you absolutely can. Towards the end of this, I'll show different deployment methodologies. The Nordic firmware is open source. You can modify it. I chose a pre-built firmware, but you can absolutely export just the raw C++ and integrate it into your application. And that's a major talking point later in step 5 there. So hold tight on that one. LoRaWAN capacity. Not out of the box, you'd have to integrate that. And like I said, I don't know if you'd want to use the Thingy 53 or the bare dev kit because of the GPIO and other interfacing capabilities for that, but definitely a good use case there. And how complex can the models be to run on the Thingy 53? So the complexity of the model, audio is going to be more resource intensive than sensor data. But you do have, an M33 core, and I forget how many megs of RAM. We could go back. It's on my Thingy 53 hardware sheet. I don't want to go back about 20 slides just because I'm fearful that I'll never be able to return back. But look up the memory capacity, and during the profiling process of the model build, which we'll take a look at in a moment as well, it will give you an estimated flash and memory consumption. So you can always tell right away how much memory your model is going to consume, and then compare that to what the Thingy 53 has on board. I wish I could remember how many megs or K of memory it has. All right, so we made it through the questions. Oh, wait, one snuck in. Can I connect it with the Thingy 91 and send data via LTE mobile using my provider SIM like Vodafone? In theory, if your Thingy 91, you know what? I'm not familiar with the Thingy 91's platform capabilities. If it's got that capability, then theoretically you could open up a Bluetooth connection from the 53 to the 91, and the application running on the 91 could be responsible for transmitting data across LTE, whatever packets come through from the 53, forward them on. It sounds possible in theory. but I'm not entirely sure. So you're gonna need to do some research. Both have BLE, so yeah. Let me see, thanks, Vasilis. So application wise, if you can code it, it should be possible. All right, let's go ahead and move on from here. So let's go on to deployment. And we kind of touched on this for just a moment with the questions. In this particular case, chose to build and deploy firmware directly to the device. In Edge Impulse, you can click on deployment on the left and type in, it'll recognize, first of all, what type of a device you already have connected and recommend the Thingy 53, or you can select it by just typing in and choosing it. And it's a little bit off the screen there in that slide, but at the bottom, there's a build button. And click the build button and it'll generate the firmware. It'll build the model. It goes through the process. It will then generate a zip file, and the zip file will automatically download, and a little video pops up that shows you how to flash the firmware. You can do it via a USB cable connected to the device. It can also be done wirelessly, but I had the USB connection attached to the laptop at the time, and you can use the NRF Connect app to choose the zip file that got downloaded, choose the Thingy 53, and click Write, and it'll just flash it straight to the Thingy 53. So your model has been packaged up and now put onto the device. Once it's on the device, now you can do live inferencing. The model's built, the model's on the thingy. Turn it on, connect it to the app again, and we can see live results coming from the Thingy 53 attached to the pump. I started off in this screenshot in the idle state, as in the power was turned off, the pump was not running. I then turned the power on, the pump fired up and began to pump the water from the tank, well, from tank to pump, pump, back to tank. But then I used that little control pad that I showed you there a moment ago, and I cranked up the speed. I trained the whole model at 10% power. But because I can increase or decrease the speed, I increased the speed, and I start to see at the bottom of the screenshot anomalies coming in. Now, I do have two samples here down at the bottom that think it is idle, so that's an incorrect classification. But the last three there, once it has sort of reached a steady state, it knows that the pump is running, but that anomaly score above 1, even above 2 on that second to last sample, is telling me something is wrong. In this particular case, the pump is going way too fast. I think I cranked it up to like 75 or 80% speed. And that's the important factor here then for predictive maintenance. That's what we want to focus on when we go to deploy at city scale and integrate with existing monitoring systems, existing infrastructure. We'll cover that in just a few minutes. So here's the part where we are going to have to hope that everything goes according to plans. Let's try a demo. Let's switch back over to my other cameras, and I will drop this screen share and instead share the Nordic app while switching my camera. Let's see if we can even figure that out. I think so. you should be seeing the thingy. And then change the video. Okay, so there's the pump. It's running. It may be a little hard to see, but it is definitely turned on and going. We'll be able to see in a moment when I turn the speed up. You'll be able to see the water moving more. Now, in the app, I have the device. It's already connected. The Thingy 53 is sitting on top of the pump over on the right-hand side of the desk. And that's the training data set. I want to come to, I've already built the model. I want to come to inferencing. And this is old inference results, but I'm going to click start. And now we should see some results come in. Yes, it is running. Let's see. We'll move the camera to that closer view just to see if we can view the LED when it comes through. Yep. Okay. So these are live results coming from the thingy. It knows that the pump is on. Now, let's take a little walk over here. Cord should reach. And crank up the speed. Switch the camera back in just a moment. Sure enough, we now see that anomaly state. And if we go back to the other camera, might even see some better movement in the water. Yeah, there we go. So we have a success, which is great because it's not even 9 a.m. in the morning yet. So that's a win for the day right there. But everything that I showed, I built here. I was able to prototype. I did it in, I don't know, maybe a couple hours of time. I think the hardest part was the physical construction of the closed loop system, getting the right fittings. Let's do this. Let me turn the speed on the pump back down. Come back to our state that the model was trained on, because I've scrolled off. Hang on a minute. And now our anomaly has disappeared. And I'll actually turn the power off. We should get down to that idle state. Yeah, there we go. All right, so we got it. Let me stop that screen share and we'll come back to the slides. Okay. Back to sharing. Back to more slides. Even come back to me at this point. I can find myself. Here I am. Okay, and we can proceed on. Quick time check. All right, we look okay. So we've made it through our first 4 pieces. Last bit here is talking through prototyping and moving to production and scaling a system using the Nordic Thingy 53 as a platform. So we just saw the Thingy 53, and it's great because it's out of the box, ready for prototyping your machine learning model and ready for projects to sort of get a feel for your connectivity and get a feel for the machine learning model creation. And you saw that I just downloaded a ready to run firmware. But that, as a standalone discrete item, is not really going to do the job at city scale. But in that deployment step, you can also download a library or raw C++, and you can then modify the firmware, which I mentioned earlier is open source. It's on GitHub, and you need to be able to then use those bits to build out your application. But the Thingy 53 is still, like I said, a turnkey prototyping system. The next logical step is probably to transition to the 5340 development kit. Because as you can see here, this board now breaks out much more I/O. You've got your GPIO, you've got your pins, you've got all your expansion capability here. And you can then use that to begin the process of integrating into existing systems, integrating into the ability, I mean, quite honestly, with toggling of GPIO pins on and off, build logic that says, if an anomaly is detected for X number of minutes and crosses a certain threshold, then kill power to this electrical system that is powering the pump, or so on and so forth. So you can then begin to prototype your interfaces to your systems. Or when you reach the final stage of your project, build a custom PCB that fits and fits your desired installation location, and really, quite honestly, only does or contains the things that you need it to do. You may not need all of the features on this development kit right here. And, it's nice that they're all there, but when you go to build a product, you get to a point where you reach custom boards all the time. Things like smart watches, smart rings, those are custom PCBs built around an SoC. In predictive maintenance for a smart city, you may do the same thing. Build a custom PCB that only contains what you need and cut down on the cost that way. The NRF 53 SoC can be purchased. You need a little bit then of work to lay out a PCB around it, but it's totally doable. It's probably the right way to go about it as well at scale. So as we were just talking about, you need to build your application that then integrates with your existing systems, infrastructure, central ops, monitoring. And because the SoC or the development kit or the Thingy 53 have BLE and Wi-Fi, you can take your inference results and transmit them bring them into your systems, your applications. We saw way back at the beginning of the slides, the energy company that's building this facility here in Phoenix, they have a central ops, they have a monitoring office, they have views of the health of the system. That's what you need to integrate into. You can also iterate and improve your model. I built one model with 18 minutes of data. That's a good start. But realistically, what you want to do is get out into the field and get one of these onto the side of the real chiller or pump, collect more data, bring that data back in, and then, I'm not sure what happened there. My slides decided to refresh themselves, but bring that data back in and create an MLOps pipeline. Let me come back to presenter view. Really know why that just decided to refresh itself. But with all that said, that is the end of today's presentation. And so I'll take a pause here and we'll come back around for a second go at any questions. Let's see what we've got. What is the MTBF, mean time between failures of these devices, the Thingy 53? I'm not too sure, Harish. You know, a Thingy 53 is a prototyping platform. It is not by itself designed for enterprise usage. That would be the SoC. So what you'll want to do is do some testing. I just don't know how long a Thingy 53 will survive in the wild, but it's not really intended to be that. Its true intention is for that very first step of prototyping and then move to the development kit board and onto a custom PCB and just use the SoC. Does Edge Impulse support other RTOS like RT thread, free RTOS? Because you can export as C++, you could integrate a model, quite honestly, into anything. There's some work underway to engage with the Zephyr RTOS. I don't know how far exactly that has come. I know there are some sample projects floating around out there. You might want to toss that question over onto the Edge Impulse forum just to get some visibility. But at the end of the day, you could always integrate a model into any RTOS applications, or however you're doing your development. Is this dev board from Nordic cheaper than ESP32 dev? Well, I don't really know the answer to that. You'll have to take a look at the price locally, where you are for the Thingy 53. I think that they run about $50 here in the United States where I'm located. And ESP32 is also going to vary. There are lots of ESP32s out there, and keep in mind that the Thingy 53 has a whole array of sensors on it. So you might be able to get some bare ESP32 board that just has simple, GPIO pins, but you don't have any of the sensors. And once you add those to the cost, you're probably right at about the same price, if not more than the Nordic. But, that's going to also, like I say, depend on availability and retail pricing where you're located. And how do I use Thingy 53 to connect to Wi-Fi router? Do you plan to add Wi-Fi connectivity to the new Thingy? Example using NRF 7002. The Wi-Fi functionality is actually under development from an Edge Impulse perspective. I don't believe it's available yet. The Thingy 53 Wi-Fi native, the Nordic native Wi-Fi capability is certainly there. And then as far as the NRF 7002, unfortunately, I'm not too sure. The 7002, I'm not familiar with. Okay, I think that's it for the questions. Oh, wait a minute. Is there a Gerber format for this dev board so we can add and sub for prototyping? I think what you might be referring to, let me see. Let me grab the thingy off of the had it attached with some double-faced tape, so it does come off. Inside of the thingy, we can open this up. It's got the plastic shell on it, and inside of it, you can access the PCB. I don't know specifically if this board, if the Gerber is available. It may be under NDA. I'm not totally sure, or it may be publicly available. So you'll need to take a look and do a little bit of research there. I assume what you're asking then is if you wanted to take this as it stands and modify it. Otherwise, yeah, like you said, you'd have to go to the dev board. And does this dev board support external Wi-Fi antenna? This one, the Thingy 53, does not. It does not have an antenna connectivity natively, but the dev board itself could always be, the dev kit, I should say, could, always be adapted. And that's it. We did it with 6 minutes to spare. Any last questions?
I think one just came in.
One just came in. Thanks, Katie. I see it. Can we use the 7002 dev kit with Edge Impulse? Not that I know of, but let me go double check the docs real fast. I don't believe it's in there. Docs. Do is move this over to, so we can write in, and we can scroll down and have a look at MCU target, Nordic Semi 52, 53, 91, 60, Thingy 53, Thingy 91. So no, unfortunately, 7002 is not in there. As it also have NRF 5340. Oh, okay. So the NRF 7002 developer kit contains the 5340 SoC. I have a strange feeling that would actually work with minimal effort. I suspect you'd be able to get that running then, yeah. It's not out of the box, but I bet you could get that going. All right, so unless there are any others, do you have any free giveaways to developers? Well, I do have this sticker, but I'm not sure that qualifies. So, anything else, Katie, or I think we made it.
I think that's it. We made it. Great work. Yeah. Thank you so much, David, for joining us and for walking us through that workshop. That was excellent.